Okay, this is about where we left off last time, right? We learned about 2's complement. Now remember, 1's complement is you just go through. I've always thought the naming was a little funny. But 1's complement is you go through and you flip every bit. So it's just like you apply not. All right? But then you add 1 to the number. And that creates a negative number. But I really tried to emphasize the fact that, like, if I wanted to, like, when I add 1 to a number, like if I have a plus b, or minus whatever, plus a minus number, it doesn't really matter, plus 1, right? Remember, when we were doing the arithmetic with 1's complement negative numbers, we were always off by 1, right? We were always like lower by 1, like 1 lower in the table. So the trick, we could just add 1 to the final result, right? So we did a plus b plus 1. Again, really it was a minus b, right? A plus a negative number, which is just minus, right? But a plus negative b, whatever. We would do that. We were off by 1, so we fixed it by adding 1. Right? Right. Right? Because remember, 1's complement is flip every bit, and then that's it. But it wasn't quite right. We added 1. So the trick we did was, well, bake this plus 1 that we were doing after the addition of a negative number. Bake that in to the negative number. And why are we allowed to do this? Because a plus negative b plus 1, this is the same thing. It doesn't matter when I add the 1. I could add the 1 before, after, whatever. If you're thinking, well, I guess you could have added the 1 to the a. Yeah, but that hasn't, no, don't do that. B was the one that we're like negating, right? So we bake that plus 1 into the 1's complement number to get 2's complement. Okay? That was 2's complement. Any final questions about 2's complement as an idea? Now, that rant was all about how we can bake the plus 1 into the encoding of the negative number. All right? But the point remains, how, where, why, and when I add a 1 doesn't really matter. Okay? When you want an encoding, yeah, it matters. You bake it into the encoding of the negative number. Okay? But when you're actually doing the operation, we could have added the 1 at the end. We could have added it in the middle, before, whatever. Okay? Okay. So 2's complement, yeah. Any questions about 2's complement? Ask now before we carry on. All right. So, negation and subtraction. Well, first of all, if I want to create a negative number, all I have to do is negate all of the inputs, not all of the inputs, and add 1. Okay, so how do I do that? Well, here's a really easy way to do it. You take your number, you invert it. Now this is an adder, it's a full adder, okay? And I want it to produce this, like the negative number, okay? So if I've got my negative number, my positive number that I want to negate, what do I, okay, it really depends on my configuration here. I could have done it in multiple ways. But what is B? When you look at this, who can tell me what B is based on this configuration? We saw this near the beginning of the semester, so you might not quite remember. This is some bit pattern based on the inputs. We negate it, it goes into A. All right? What does this give me? What is the, who remembers what this symbol is? Pull down resistor, which means it's like 0. Okay? And then we take 0 into 8 bits, put it into one signal line because it's an 8-bit adder. So we've got B is 0. So we negate the A, we add 0 to it, but what am I adding in to carry in? Remember, carry in is only 1 bit wide. Either we carry something or we don't. What is this called? A pull-up resistor, meaning its signal is what? 1. So, based on the inputs of this full adder, we have A, which is the complement of the input, B, which is 0, and then we add 1, because carry is high. That negates. Here. And I want to show you something real quick here. Up. No. No. Numbers. 2's complement. Negation. Okay. So here we go. So, by the way, I do switch in the course because this can be a little confusing to people. Not confusing, but there's more like circuitry involved. Like you have to know a little bit more. One thing that you might see me use is, pay attention to this. This is big. You're going to see it. Is constant values, where you can set this to be a 1 or a 0 or really whatever you want it to be if it's a multiple bit input. I left it like this to make it a little bit more low level to like what the circuitry is. But I can set this to 1. And I could even have, so like this. No. There. Oh my goodness. Just go with it. And I could have done this, but like how many data bits? 8. And we give it 0. There. And now when I run, oh, what did I do wrong? See? Data bits 1. What did it say it was mad?
I think it's touching one of the.
Oh, there. Yeah, I think you're right. Delete. There. All right, there we go. So now, what is this? Let's do a smaller number. 5. And is this, I'm guessing this is -5. Right? 1, 1, 0, 1. Let's go back here and look at the table. Perfect. And remember though, like the leading ones, right, is like negative. Now, you of course might notice that's not -5. That's 255 minus 4. That's 251. Yes. It's the same bit pattern. 251, I think that's what this is, 251, right? 255 minus the 4. Yeah. Let's verify. 251 in binary. Yes, perfect. 1111 1011. Perfect, yes. So, pay attention. You say, how am I supposed to know if that's -5 or 251? Who can tell me? Based on seeing this bit pattern, how do you know? That's the only way to know. If you only saw the bit pattern, there's no way to know. Because remember, It's an encoding. And if I don't know how to decode it, I can't decode it. Do I decode it as a negative number? If I do, it's 250, or it's -5. Do I decode it as a positive number? Well, then it's 200, wait, -5, yeah, 251. Do I encode it as a decimal number? If it is, it's 1, 2, 3, 1, 2, 3, 10 million, oh no, 11,111,011, right? Like, I don't know. Now you might say, how, but there's no, I know, I'm just saying they're ones, right? The point is, I don't know. And this is something we need to be careful of. All of our modern programming languages have the types built in. The computer knows, oh, this is an integer, so I decode it as an integer. This is a character, I decode it as a character. This is an unsigned integer, so I can, like, it knows. But there was a time where, like, Fortran invented types. Before that, you had to know. You had to do all of this extra, like, bookkeeping in your head, which is fine, but it's one of those nice things that you bake into the language, and it takes care of it for you, which is nice. But at the end of the day, it's just high voltages and low voltages. That's all it is. That's it. I don't know if it's a -5 or a 251. I would have to know strictly by the context. What am I doing? And even then, we might trip up. If I've got two numbers and I add them together and I see this, I may have added a negative number, right? And if I added a negative number, I may have gotten a negative number. But I don't know. Maybe I added two positive numbers. And if I did, maybe I got 250. The point is, I don't know. Even if I do know the context, I got to be careful. So, point being, it's just signals. We have to be very careful and be very aware of our data and what we're doing. Make sense? As much as it can, at least? Yeah. So, anyways, how does this work? Remember, one's complement, that's this part. The input, invert it, not it. This right here, you're like, that's a 1 not, yeah, this is an 8 input not. Whoop. It'll not every single bit on that line, which is nice. We not it, and then we add 1. How do we add 1? Well, the thing plus 0 plus 1, we added 1. And then this gives us our result. Cool? Cool. Any questions, thoughts, concerns, or anything? Yes?
Does bit 7 have to be a 0 so it's a positive number?
If, I don't know. Because at the end of the day, if I have, and I know I have a signed integer, yes. If I know it is a signed integer, if I somehow magically know I have a signed integer, bit 7 would need to be 0 to know it's not negative, because it could be 0, right? Like these could all be 0, right? So that's a good point. If it is a signed integer, and I know that that bit pattern is a signed integer, when this is a 1, I know, when the most significant bit is a 1, I know it's a negative number. But if I don't know if it's signed or not, if I had the bit pattern 1, 0, 1, 0, like 1, 0, 1, 0, no, 0, 1, 0, 1, 0, 1, 0, 1. What is that? Well, that's 55 in hex. I know that. That's easy. I don't know what that is in decimal, though. I don't know offhand. We could find out quickly. But the point is, this bit pattern will mean, I think you might be right. This bit pattern, you know that because it's on the assignments, because I love these I love this bit pattern, and I also love this bit pattern. Why? I mean, just look at them. I don't know, but if you add them together, you get 255, that's for sure. How do you know? Well, look, you just, you know.
Well, the first 4 bits give you 10. Well, they're both 10, so we just multiply 10 times 16
There you go. 10 times. Close, but yeah, look, this would be 1, 1, 1, 1, 1, 1, 1, 1.
The second one is like, it's 10 times 16 plus.
Yeah, I gotcha. So, anyways, the bit pattern 0, 1, 0, 1, 0, 1, 0, 1. What is that? Well, what is that in see if we can find them. No, I don't. I want to add the binary to decimal. 1, 0, 0, 1, 0, 1, 0, 1, 0, 1 is 85. And it's telling me the complement. But no, I want. I suppose the problem is if it really is when that leading one is, whoops. This is all to say, if I don't know if I have a signed or unsigned, when it's a 1 at the beginning, it might be positive, it might be negative. That's all. If it is a 0, well then I guess it must be a positive, right? Either way.
It's because if you have an unsigned, if you have a signed integer, I mean, it should, you have the same number of integers on both sides of 0. Right, and every bit doubles the number of.
Yeah, but okay, so 0, 1, 0, 1, 0, 1, 0, 1. Okay, if this is signed, I know it must be positive though, because this is not a 1. If it's unsigned, well, it doesn't matter. It doesn't matter. It is what it is. Yeah. So there's still ambiguity, and that leads to a problem. We just have to be careful about what we're doing. Another thing that gets tricky is like, soon we're going to be talking about like, what can I tell about if I want to know a number is 0, how can I do that? Well, I can ignore all the bits, right? Because think or, nor. Nor is only true when everything is 0, right? Or is true whenever it's not, whenever there's no inputs that are always 0, right? Remember, or 0, 1, 1, 1. This would generalize to more inputs, right? Nor is, well, 1, 0, 0, 0, right? So if you nor all of the inputs, and you get a 1, then now I know the number is 0, okay? But, like if I add the number, if I have like 1 plus 255, 1, 2, 3, 4, 1, 2, 3, 4. Yeah. Right? And I do that operation, what do I get? Well, I get, okay, 0 carry, 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 1. But if I have 8 bits, we lost it. Now, the carry bit, the carry out would be high, right? Which is cool, because sometimes it's nice to know, did my operation produce a carry that I can't keep track of? So the carry bit would be high. But also, oh, the result 0. But was it 0? I mean, it kind of was, it's 0 because we lost it. Really, the answer was 256. But as far as the circuitry is concerned, if I nor all this together, it tells me that the answer is 0. Right? So was it 0? Kinda. Did we have a carryout? Yeah. Now, who can tell me what this number is in 2's complement? What is this negative number? Assume this is a signed integer. -1. What is 1 plus negative 1? 0. The arithmetic is done the exact same way. And of course, 1 plus negative 1 is 0. But by virtue of how the addition works, the carry bit would be high. Ugh. Now we have the opposite problem where, 256, is the answer really 0? No, but there was a carry bit. 1 plus negative 1, the answer is 0, but it produces a carry. Was there really a carry? Ugh. This is a problem that we're going to hit a little later in the course. But it's not really a problem. It's just another case of we have to be aware of what we're doing. We got to keep track of this stuff. Anyways. So that's how we can negate a number. Now, okay, in the above example, the input bits are flipped with a naught. And then here the full adder is adding 0. And we're setting the carry bit to 1 because that's an easy way to add 1 to something. So now we could actually, let's do this. Create a slightly, here, I'll just open it up and go away. Open, discard, subtraction. Now, we could actually modify our full adder to be able to do subtraction. Give yourselves, I'll explain it, and then I'm going to give yourselves a few moments to think about it, okay? A. So imagine I had the number A and B, and I want to add them together. What do? Well, I take A, B, I input it into here. Now, I know you're going like, well, what's all this? Just wait a moment. That's the magic subtraction stuff that we're going to look at in a moment. A and B produces the output, right? It's an adder. Nothing special. But if I want to do A minus B, well, remember, A minus B is the same as like A plus the negation of B, right? This shouldn't scare anybody. 5 minus 2 is the same as 5 plus negative 2, right? Think back to grade 2. Maybe grade 3, I don't know. So what we're going to do is we're going to just negate the number. We're going to do addition, but just negate the number. How are we going to negate it? With that 2's complement idea. Invert the input and invert the input and then do the addition. By the way, who submitted the poll request last night? Who was that? It was you? Well done. Good catch. Very good catch. In fact, I was like, oof, that was a bad mistake that I put in there. Everyone was going to get it wrong. Speaking of, look, we've got a bit inverter. Did anyone start assignment 2? No. Just this guy right here then, I guess. Good, because there was a mistake in it that would have made question 1 not really possible. And question 1 is about this exactly. We're using an XOR. Now, first of all, we've got this new signal here called sub. We're going to call it a control signal. It controls whether or not we're doing subtraction. So, the first thing we can see here is, okay, sub is going down into the carry. When it's not on, we are adding 0 to the carry. When it is on, we are adding 1 to the carry. By the way, if you're saying, oh, so this is the circuit to do subtraction, this is a circuit to do subtraction. I'm not saying this is particularly a good one. These designs are specifically chosen to demonstrate ideas, but we can do subtractors different ways. In fact, if you go into digital, there's a subtract. Like it's just there, whatever. But anyways. So when subtract is on, I want to do subtraction. So to do subtraction, we need to do the 2's complement thing. Well, sub, that signal will turn the carry to high, meaning, okay, add 1. But like, what's going on here? And I'll give you 30 seconds to look at this, think about it, and see if you can make sense of why that matters. Like, what is that XOR doing?
shake it.
Yeah,
It'll almost never go away.
it forms like a nice like membrane. Yeah. What kind of auto blender do you have in there? Is it a ball or is it the thing at the top? Ooh.
I find it would well, I'd always have to clean it afterwards.
You're not wrong, but yeah. So like, what is that XOR doing?
It's basically just inverting it.
Exactly. It's a controllable inverter. Think about it. It's XOR, right? We have some B signal, and then I'll call it S for like the sub, okay? It can either be 0, 1, 0, 1. And the B can either be 0, 0, 1, 1, right? What functionality do I want here? Well, okay, look, it's XOR. So we know what we're going to get. We're going to get 0, 1, 1, 0, right? If B is a 0 and the sub is off, we get a 0. Let's just go down here. We're going to skip this one. If B is a 1 and sub is off, we get a 1. If the subtract signal is not on, it just relays what was there. Okay? But if we turn that sub signal on, it inverts the input. If we see a 0, we get a 1. If we get a 1, we get a 0. So we are using exclusive OR as a controllable inverter. When this is on, I invert these inputs. When this is off, I just leave the inputs alone. So XOR, if you think about it like this, you've got a control, like you've got a bit inverter, which is pretty cool. Which is question 1 on the assignment. Spoiler, yeah. It's pretty neat, right? Yeah, there we go, cool. So, what does that mean? Well, when this is on, we invert the inputs and we add 1. So this is 2's complemented. So we add the negative, we get the result in there. Any questions, thoughts, concerns, comments, anything? Everyone's happy? Sad? No questions, really? Is it because it's so, y'all are really quiet. Is it because it's so simple? Like it makes it so easy? Or is it because it's so scary you're confused? I'm so good at this, I know, thank you. Who said that? I want to know who to give extra points to. Perfect. All right, cool. So there is our adder that can now do subtraction, which is awesome. You might think like, okay, if I can do addition, okay, look, we've got a, there's always this like hardware software thing. If I have a minimal but complete set of hardware, I can make software to do whatever I want. If I have like an adder, okay, I can do multiplication, right? Because if I'm like, if it's 5 times 5, well, I just do like plus 5 times, like I loop. Just do a loop. Do addition 5 times by looping, right? But of course, when you do that, like how many steps, how many floating point like how many operations are required? Well, if I'm doing like 5 times 5, I have to like add 5 times, right? So there's like a cost there. Not a big deal, but when we do something in software, like, okay, it might take a couple of instructions to do the multiplication. But if I could magically build, like let's see if digital has it built here. Because we have a multiply component, like what's going on there? So So can we open? Where would we find a, like processor? Maybe processor? No. Multiply. Okay, well, they're using multiple full adders. So they're kind of. But the point, like, you can see that they're doing something in hardware. I'm guessing this is just using the multiply. Oh, no. The point is, like, there are some things, like, you can make the hardware to do something, and that might not take multiple, like, clock cycles. Or you can make a minimal set hardware, but then you can do things in software. There's always this, like, cost-benefit analysis. It's going to cost a lot more to make a multiplier piece of hardware, but it would make our computers faster. So you can have specialized hardware for certain operations that speed things up, but that could cost you. You know, there's always these considerations. All right. Yeah. Any last questions before we move on to the ALU and the ESAP? It is getting crazy. Now we're real cooking. No questions. Okay, so the ALU and the ESAP. Have I said ESAP yet? Okay, cool. I'll describe that in here then. Okay, so the ALU is a combinational logic circuit for integer arithmetic and logical operations. We're not doing any float stuff. Floats are annoying, okay? So in this world, everything's discrete, no decimals, all right? And notice that I said it's combinational. There's no, like, sequentialness to the addition, right? The addition didn't require multiple clock cycles. It just needed, like, as soon as the ALU, like, as soon as those series of gates that were doing, like, the full adder gates, got the input, it produced the output. There was no, like, not like a register, which took a moment, like, it needed clock cycles to get stuff into it. So some things so far require clock cycles, some don't. And that's fine, but we just got to be aware. So the ALU is a combinational logic circuit. It doesn't actually require any, it doesn't require, like, additional, like, multiple clock cycles. So the idea of the ALU. So this is a generic, listen to me. The adder is not an ALU. An ALU will have an adder in it. Okay? It's a part of a bigger thing. Does anyone know what ALU stands for? Yeah, there you go. I guess yeah, ALU. I've been calling it ALU when I actually called it ALU. Oh, this should be an uppercase L for consistency. Someone's got an easy pull request there if they want. Anyways, the idea of the ALU. Okay. This is a generic symbol. Okay? Operand, operand. Opcode, that's like the operator. Okay? So I give this magic component two values, and then maybe I say, like, add them together, and you get the result. Subtract them, you get the result. Do logical OR on them, you get the result. That's what this is. So it has 1, 2, 3 inputs, and it produces an output. But of course, you look at this and you're like, well, no, hold on, there's the status and a status thing. Yes. So I know who's had me before. And who knows how much I talk about side effects being bad. Yes, you all know this. Side effects are bad. We don't like side effect things. We like pure functions. For those of you that don't remember, a pure function is a function that takes inputs and produces its result. That's it. Something with a side effect is like it takes inputs, it may or may not produce an output, but also I change some RAM somewhere else, and I change some values somewhere else. Like side effects, yeah, yucky, bad, right? A side effect would be something like def list a dot append 7. Something stupid, right? But there, that is a function with a side effect. Why? Because it got reference to this list, and it modified that list. It didn't return anything. Ugh, side effect, right? Is it bad? No, but it's a recipe for trouble. Avoid side effects, okay? Now, you look at this. We got some side effects. Sometimes an operation results in like a carry bit happening. And sometimes it's important for our computer to know, did the operation I just do something noteworthy, like produce a carry bit, produce a 0, produce a negative number, etc. Sometimes that's important to know. So the ALU produces the result, but it also might keep track of I just got a 0. And this is remarkably important for our system. Further, the status before the operation, like did the operation I just do produce a 0, might be important for how this operates. Okay? So this is the side effectiness here. Now, how do you resolve this conflict of like, well, he's always talking about side effects being bad. When we are operating at such a high level, like in Java or whatever language we're using, we have the luxury of not having to, like, we can avoid side effects at all costs, right? But when it comes to this low-level stuff, we're kind of like, it is what it is, okay? So we just kind of have to deal with it without going deeper into the philosophy of side effects. So with sophisticated ALUs, some operation is applied to the input operands to produce some output. The operator is specified with some opcode passed to the ALU. Our ALU is going to be far simpler than this like very general idea. Our ALU is just going to do addition and subtraction, all right? So our opcode is basically, are we doing subtraction or just regular addition? Okay, that's what it's going to be for us. But these sophisticated ALUs might have things like, well, I can do addition, subtraction. Sometimes an increment decrement is handy. That's a nice little operation that you might say like, well, that's the same as adding 1. Yeah, but there might be some circuitry that makes it like more efficient. And or not, XOR, some stuff. Bit shift, rotates. Does anyone know what these are? Effectively, yeah. Bit shift is if I have 0, 1, 0, 1, and you bit shift 1 to the left, that becomes 1, 0, 1, 0, right? If I bit shift 2, that would become 0, 1, 0, 0. Okay? But it gets padded with zeros. Similarly, if I did bit shifts to the right. But then there's also rotates, which means like, well, that would have actually produced, like if this was a rotate, these go back there. These operations are handy for a variety of reasons, but we're not dealing with them with our implementation at this stage at least. Did you have a question? No? Okay. All right. The ALU may update the system's status flags, things like, did my operation do something noteworthy that I might want to keep track of later? By the way, these status flags are very important, but yeah, we'll talk about them a little later in the course. Yeah, that may have effect on, yeah. Anyways, for example, the system may remember the last operation outputted 0. The status flag are a topic for later. Digital does not have a built-in ALU. Like if I go into here, component, like there's no ALU here, but you can load up a custom, like you can somehow, maybe update, no.
Import like whole files.
You can, I just don't remember how right now. Library? No. So, okay, there might actually be an ALU in one of these. Arithmetic? One of these might be an ALU, I don't know. Actually, I'll talk about those now because we don't really have time to get into the ALU fully. But there is a import. There is a way to import a circuit, and you can actually input one of the, like, okay, open, open. ALU. I don't know, I'll just go with this one. ALU, open, great. So this is like an ALU, okay? And it's a beautiful design. A, B, opcode stuff, okay? But look, it's just like, okay, am I doing add, subtract, and, or, exclusive or, not, negate, I don't know, swap, I don't know what these ones are, multiply, there's a multiply down there, that's cool. And it's just these giant demultiplexers, or no, a giant multiplexer that says, well, like which opcode am I actually doing? And it selects and it produces the output. Like it's just a series of all of these like, operations that we might want to do. That's really all it's going to be. Ours is this. I mean, it's kind of like these two, except we hacked our own subtract on to the adder effectively. You can import this into, what's cool about digital is you can make circuits importable, and when you import them, you can even like select a special symbol for them. And if you do in digital, no, you would see this. By the way, like it's got a special symbol, which you're like, hey, it's like that. Yeah, it is. It's just the other way. 0, negate, or negative, carry. Hey, look, those are the flags. Those are the status flags. Those are the status flags we're going to use. Although we call negate the significant bit because, again, you don't know, is it really negation? I don't know, because was it signed or unsigned? Ooh. All you can do is really observe the most significant bit and try to determine what's going on. Anyways. Digital does not have a built-in ALU like the other components. However, it does have a custom ALU you can import. This ALU will not be used. We're not using this one. We've got a simpler one. But the general idea is, as I just showed you, remarkably straightforward. Just you series them up. All of them receive. What's kind of cool here is it's kind of like RAM. Remember how RAM, everything was outputting. It wasn't like we were turning on one of the functions. Here, we're not going to turn on one of the functions. All of these circuits are always calculating the result. It's just all of the results are on their output signal lines, and then whichever one we actually care about, that's what we're going to turn on. Okay? In the same way like RAM. All of the rows were like outputting, but RAM itself only output the specific row through a multiplexer. Right? Yeah. Anyways, the general design is pretty simple. Now, one thing. Now here, I was talking about 74XX. So there's like these series of little like chips called 74. A lot of them are LS, but they have different like codes. Like 7480. 7482, 7483. There's all of these, like the 7400 series, okay? If you go you will find a giant list of, where are they? There you go. You want to find like, oh, I want a hex inverter. I want a 4 input AND gates, 4 2 input NAND gates, and then all of these, like you can go find these chips, okay? Originally when I was designing this course, I had these chips in mind, and then I realized that was a bad idea. So like here, a quad 2 input AND gate. What that means is we'll have a chip that has 4 2 input AND gates on it, okay? So we're going to look for 7408. Let's do new. Component, basic, 7408. There, right? You know, you've seen these chips before, right? I mean, here it's like, it doesn't quite look exactly like this. It's a little black thing, right? But it looks like this. This you hook up to some voltage. This you hook up to ground. And then we have 1A, 1B, Y. So this is like input, input, output. Okay? In fact, for the sake of fun, and we're going to have, okay. Ground. Ah, shoot. Okay, crap. Okay, whatever. If I were to go like, this is, it's just AND. It does AND. Okay? And they have a common form factor. All of these chips, a lot of them have, what is it, 14? 1, 2, 3, 4, 5, 6, 7, yeah, 14. But some are bigger. They can be bigger depending on what they're doing. But they have a common form factor where this is always ground, this is always high, and depending on these. And this common form factor is really nice for engineering purposes. Like if we go and we see like here's a drivers, okay, right? Like, oh, okay, based on what we've got, right? All these different things, right? Anyways, yeah. Why would, yeah, that's what these chips are, okay? Depending on what the code is, they'll have different circuitry inside of them. They can become very complex, they can become very simple, but this is what they are. Sometimes in digital, oh, look at that. Look at that, the driver. Hey, you know how we were trying to figure out how to do drivers with transistors? Look, that's what they're doing. That's not really what I meant, though. Shape. You can change it to like a simple view, so it just kind of looks like that. But at the end of the day, they're the 7400 series. And that's that. All right, cool. We'll stop there. See you all later.